Continuing our discussion on the three forms of equation of a plane. Now we want to look at these very simple planes, the xy, the yz, and the xz plane. So let's look at the first plane, the xy plane. Where is the xy plane? It is here. Where is the xz plane? It is actually here. And where's the yz plane? It is actually here. If you recall in the earlier example, we managed to write down the equation of the xy plane in the first form. R equals to, in the first form you need three vectors, remember? Three vectors. The first vector is a point on the xy plane. A convenient choice would have been, remember, we use this. You need a vector that's parallel to the xy plane, a good choice. And then next one. Now, if you want to write down the equation of this plane in the dot product form, you need r dot, right? You need a vector. Now, bear in mind, this is always a vector that is perpendicular to the plane in question. In the case of the xy plane, what do you think is a vector that is perpendicular to the xy plane? Look at the diagram. What do you think? You will see that a vector that is perpendicular to the xy plane, the good choice would be a vector that's along the z-axis, and this would have been 0, 0, 1. You could have actually taken this vector to cross with this, and you get also a vector that is perpendicular to the xy plane. But for this case, you can also see it geometrically. You don't have to do any cross product actually. Then now to find this number on the right, you always take the point on the plane, the dot product with this, and because this is triple zero, the dot product will yield 0. And then from here, right, from here to convert into the third form, you write this as xyz, the r as xyz, you perform the dot product, you get the answer z equals to 0. Next, how about the xz plane? In the case of xz plane, again, to write the vector equation in the first form, I again need three vectors. Alright, once again, this represents a point on the given plane. A convenient choice would have been just 0, 0, 0. And then a vector that's parallel to the xz plane is 1, 0, 0, and then got 0, 0, 1. And the next thing is to convert it into the dot product form, r dot. Okay, in the case of the xz plane, to have a vector that is perpendicular to the xz plane, a convenient choice would be just 0, 1, 0. And then to find this number on the right, you take this vector dot with this, you get 0. And then to convert into the Cartesian equation, just replace the vector r as x, y, z, and perform the dot product, you get y equals to 0. Right, you write this as x, y, z. Dot product means this times this plus this times this plus this times this. You just get y equals to 0. And lastly, in the case of the yz plane, you need again three vectors for the first form. Once again, in the case of yz plane, a convenient choice will be this, and this would be 0, 1, 0, and the 0, 0, 1, right? Vectors that are parallel to the yz plane. And the next thing is to convert into the dot product form. In the case of the yz plane, a vector that is perpendicular to the yz plane, a convenient choice would be 1, 0, 0. Can you see this is a yz plane, right? vectors along this direction, right, will be perpendicular to this plane. And likewise, to find this value, right, you can take 0, 0, 0, dot product with this, you again get 0. I want you to notice something though. In these three planes, because they pass through the origin, you find that this right side number, they're all 0. And now to convert this into the Cartesian equation, again replace this r as x, y, z, and you perform the dot product, you get x equals to 0. And there you are, the three planes, and correspondingly the three different forms of the equation of these three planes.